So let's start by remembering what an identity is. An identity, again, is an equation that is always true for no matter for regardless of what value you may plug in or whatever the variable might be. And what we're going to do in this lesson is we're going to focus on trying to verify trigonometric identities. And there is a process for doing this. And I just want to be very clear that it's not the same as solving an equation. So we're not necessarily going to be trying to just simplify or using inverse operations. In fact, what we don't want to do is any operation that affects both sides. What we want to do is we want to work exclusively on one side and rewrite one side to show that it's equal to the other. And why is it that we want to work just on one side? Well, if we work on both sides, that is to say, we start manipulating both sides of this equation, we will only show that if this starting equation is true, then we can arrive at some other equation that is also true. But we will not have proven that the original equation was actually logically true. And so for this reason, we're going to work exclusively on one side. Whichever side that is, it's up to you. It doesn't really matter. But there are a couple of guidelines on verifying that I think might be helpful. It's always a good idea to try to start with the more complicated side. And mathematically speaking, we've had a lot more practice working with simplifying complicated expressions and making it more simple than it is to take something that's already pretty simple or condensed and to try to expand it out. Oftentimes, we will need to factor, square, or add up fractions or combine fractions. Um, and whenever it's possible to use an applicable identity, that would be oftentimes helpful. And it's also a good idea to remember that every trig function can be rewritten either in terms of sine or cosine. Remember, tangent, for example, is sine over cosine, so it has both. But cosecant, for example, is just the reciprocal of sine. So that might be a good way to often get something like a common denominator when we're trying to verify. And the last one seems a little bit silly, but it's true. Just try something. There are many times where I've tried to verify something, and just by throwing in a substitution that I don't think will really have any relevance, um, substituting one trig function for another oftentimes leads me down a path of actually being able to verify. So let's try this first example here. We have secant squared theta minus 1 over secant squared theta. And we're setting it equal to sine squared theta. And we're trying to verify that this is indeed an identity. Now, what you don't want to do is multiply both sides by the denominator. Again, we can't do anything that affects both sides. So let me actually write this in red. You wouldn't want to do something like secant squared theta to get rid of the denominator on this side. That would be a valid algebraic operation if we were trying to solve an equation, but right now we're trying to verify. So we don't want to do that. Instead, let's go ahead and think about which side we'd want to work on first. And I think the left side makes the most sense. Again, we want to start with the more complicated side, if you will. So by looking at this here, there are a couple of ways that we could do this. We could go ahead and use a Pythagorean identity to rewrite secant squared theta minus 1 as tangent squared theta. And in the denominator here, I can rewrite secant squared theta as 1 over cosine squared theta. And we're setting this equal to sine squared theta. And in the next step here, we can then rewrite this tangent squared theta as sine squared theta over cosine squared theta, because tangent is equal to sine over cosine. And if you're dividing by 1 over cosine squared theta, this is equivalent to multiplying by cosine squared theta. And we're pretty much on the home stretch here. We can then say that this cosine squared theta will divide out with this cosine squared theta. So sine squared theta is indeed equal to sine squared theta. And we're done here. Now, the right side was actually just sine squared theta, but something notation-wise that I often allow with my students is to just go ahead and draw an arrow so that we don't have to write sine squared theta with every single step. But these equal signs absolutely need to be there every single step of the way. Okay, so look at what we've done. We've just shown that the left side is indeed equal to sine squared theta. And this verifies that this original equation is indeed true. And again, there's more than one way to go about doing this. If, for example, I wanted to, let's just redo this problem maybe another way. Let's say I wanted to take this fraction and actually split it up into two different fractions. That is to say, write this as secant squared theta over secant squared theta minus 1 over secant squared theta. Now I've got 1 minus cosine squared theta. And this is a Pythagorean identity that says that this is equal to sine squared theta is equal to sine squared theta. So there are multiple ways that we could go about verifying here. But as long as we are working on one side to show that that side is indeed equal to the right side from what is in the original equation, then we're good. Okay? And let's try some other problems here. Let's try something like number 2. We'll have something like this. Take a moment, pause this. This is actually a pretty short verification. We'll notice here that sine squared theta plus cosine squared theta is equal to 1. Cosine squared theta can be rewritten, secant squared theta can be rewritten as 1 over cosine squared theta. And this can divide out. Now we got 1 over 1 is equal to 1. And last time I checked, 1 divided by 1 is the same thing as 1. So that's a pretty short one. And I'm highlighting here that we can do some type of operation to the numerator and do some simplification to the denominator in the same step. That's fine. But we wouldn't be able to just jump straight from this to this. We would have to show those corresponding steps. Okay? All right, let's try one where we actually want to combine some fractions here. So do kind of the opposite of what I showed in a few other examples. So there's a couple of ways that we could go about doing this. One option is to just combine these fractions so that I have the same denominator. That is to say, I'm going to multiply this by 1 plus sine theta over 1 plus sine theta. So that would give me 1 plus sine theta. And in the denominator, 1 plus sine theta times 1 minus sine theta, well, that's just 1 minus sine squared theta. And I'm going to do something similar here with the second fraction. I'm going to multiply this by 1 minus sine theta. And in the denominator, 1 plus sine theta, again, times 1 minus sine theta. There's a common denominator. And then now when I combine these fractions, we have 1 plus 1, which is 2. Sine theta minus sine theta, that's just 0. All of that is over. Let me actually write that 2 in the center. 1 minus sine squared theta. And 1 minus sine squared theta, if I apply the Pythagorean identity, I know that that is equal to cosine squared theta, which is then 2 times secant squared theta. And there is our verification. Okay. All right. Let's do an example now where we don't want to be too quick to multiply. I know our first glance might be to start multiplying these out, and actually this will work if you wanted to just multiply this out, but something that might be a little bit more efficient is to actually apply any identities before we do any multiplying, because tangent squared x plus 1 is actually just equal to secant squared x. Cosine squared x minus 1, all of this is equal to negative sine squared x. This would be 1 over cosine squared x times negative sine squared x. And this is negative sine squared x all over cosine squared x. And using the quotient identity, we can say that this is equal to negative tangent squared x. And there's our verification. We've just shown that the left side is indeed equal to what we have on the right side. Okay. Sometimes there will be certain cases where there are no fractions to add, no products to find, no opportunities to use any Pythagorean identities. So this is one of those cases where it might make sense to actually rewrite our trig functions in terms of sine or cosine. So for example, in this first one here, we notice that tangent is equal to sine x over cosine x. Cotangent x is cosine x over sine x, which we then, if I want to combine these by multiplying both of these fractions by the other denominator, I've got sine squared x over sine x cosine x. And the second fraction, if I multiply this by cosine over cosine, I've got cosine squared x over sine x cosine x. And by adding up these two fractions, sine squared x plus cosine squared x all over sine x cosine x, and that's just equal, all of this is just equal to 1. So I can then rewrite this as 1 over sine x cosine x, and I'll just use the arrows from here on out. 1 over sine x times 1 over cosine x, being careful again to put my equal signs, and that would just be equal to, and I could actually swap these around. This would give me cosecant x times secant x is indeed equal to cosecant x secant x. And that's my original. I can switch the order of those trig functions. That's not a problem. Okay. All right. Go ahead and pause the video and see if you can work through this one. One of my hints is to think about using the conjugate here. All right. I'm actually going to work with my right side here. I'm going to multiply cosine x times 1 plus sine x. And in the denominator, that's going to give me 1 minus sine squared x. And you may not have done it this way, but this is what I think makes the most sense for me. Cosine x times 1 plus sine x all over cosine squared x using the Pythagorean identity. And I can divide out the cosine with this cosine here. And so I've got 1 plus sine x over cosine x. And I'm going to split this up now into two fractions because I know that I want to ultimately end up with a secant and a tangent. Both of these have cosine in the denominator. So I'm pretty close. So this gives me this now, which I can then finish off by saying this is equal to secant x plus tangent x. I'm going to draw my arrow to show that these are all equivalent to that, but I do, in my last step, want to say that this left side is indeed equal to what I've shown there on the right. Okay? All right. Let's do a little bit more verifying. Actually, I think that was oh, there it is. Let's do this problem here. Okay, so for this one here, we've got cotangent squared theta plus over 1 plus cosecant theta. And we want to show that it's equal to 1 minus sine theta over sine theta. Go ahead and pause the video and see if you can work this one out. All right, if you had a chance to work on it, I'm going to actually work on the left side. You could have worked on the right. Doesn't really matter. Oops. I want to multiply by the reciprocal or by the conjugate of that denominator, which just gives me a difference of squares. So then this allows me to say that this is equal to negative cotangent squared theta. And you can see we're going to do something pretty similar to what I showed in my previous example. So then this would be negative 1 plus cosecant of theta. And in this case now, because I want to end up now with sine in my denominator, I'm going to rewrite this negative 1 as negative sine theta over sine theta. And this cosecant of theta as 1 over sine theta, which then allows me to combine these two fractions. Write this as 1 minus sine theta all over sine theta. And there it is. Okay? And hopefully this helps you get a sense of exactly the rules and the process for verifying trigonometric identities.